Okay, hello everyone. Good morning, all of you. We'll start with today's quote. It says, ability is what you are capable of doing. That's what we call it as ability. And motivation determines what you do. Okay, you have some ability, but you do something because you are motivated to do that thing. And the attitude determines how well you do it. Okay, it is not enough you do something, but how well you do it. It depends on your attitude. And today is birthday of one scientist, Kroko, and he is a pioneer in aeronautics and space science who designed revolutionary airships and patented an early cyclic pitch design for helicopter rotors. Okay, he worked a lot in that aeronautics, mainly airships and helicopter rotors he has worked on. And here I don't know whether you came across Kroko. Anybody came across this name Kroko? Mathematicians. Kroko's theorem. Have you heard about it?
No, sir.
No, sir.
No. Okay. There is a what is called as Kroko's theorem. This is also, I think, maybe sometime I will spend a few minutes on that. So it relates fluid dynamics and thermodynamics. Okay. So entropy and enthalpy and vorticity, these are related, and we get what is called as Kroko's theorem. And the Kroko's theorem is proposed by the son of this person. Okay, so that fellow also is a scientist. Okay, while the design of helicopters was in its infancy, Kroko recognized that a way to change the pitch cyclically on the blades was needed if a helicopter was to work properly in forward flight. So he designed a number of airships in the early part of the 20th century and switched to designing rocket engines in the 1920s. And Kroko founded the Italian Rocket Society and made many contributions to the theory of spaceflight. He calculated that a spacecraft could travel from Earth to Mars and perform a reconnaissance Mars flyby without orbit and return to Earth in a total time of about 1 year. So if you see in the Wikipedia, you can see that he has proposed a 1 year tour from Earth to Mars to Venus and back to Earth. And how it can use the fuel is it gets the energy from the gravitational force of Venus and Mars, and it gets the energy and comes back. So he has designed something, and he told within 1 year you can go like a tour to the Mars and Venus, and you can come back. So he is Kroko. So we have this, this CMT. With my old habit, I have written
Sir,
CFD.
one doubt. Sir.
Yes.
Sir, whether Croco number in GDJP was given by him, sir?
No, Kroko theorem only. Kroko number, I don't know. Kroko's theorem, it comes something like this. It comes like V cross omega is equal to B del H naught minus T del S. This is the way we get that. So it uses TDS relation, and here it uses the stagnation property. So this uses fluid dynamics. Because V cross omega, how we get is, if you remember, once we have taken V dot del V is equal to del of V square by 2 minus V cross omega. Okay. So this del of V square by 2 is equal to del P by rho from Bernoulli's equation. Assuming it is steady, inviscid. And TDS is equal to DH minus VDP. VDP means del P. Okay. So these are combined to get this particular equation. This is called Kroko's theorem. Okay. So we'll have this hyperbolic grid generation technique today. So in the last class, we have seen what are the desired features of a grid generation. There should be one-to-one correspondence, there should be smooth distribution, and there should be possibility for clustering, and the two uh, uh, grid lines should not intersect each other like that. And then we have seen the types of grids, and we have seen the types of domains, that is simply connected, doubly connected, and multiply connected. So if there are no bodies in the domain, we call it as simply connected. If there is one body in the uh, domain, we call it as doubly connected. If there are multiple bodies, we will have multiply connected. And types of grids we have seen fixed and adaptive, and uniform and non-uniform, and structured and non-structured, like that. And then we have seen what are the grid generation techniques. So we have seen conformal mapping and algebraic techniques, and then PDE techniques. So here we have again elliptic, hyperbolic, and parabolic. Okay, these are the various things we have discussed in the last class. And conformal mapping, I told this is outdated. And algebraic, it is very simple and very fast. So they are the advantages. Disadvantages, the discontinuities. If there are discontinuities, it will not work. And so here clustering also is possible, like that. So we have seen various examples for algebraic grid generation, like if there is a diverging nozzle, or if there is a flow over a flat plate. And we have seen the relations, how to cluster based on a parameter beta in that. And if there is a channel, if I want to have clustering on both sides of the channel, because walls are there on both sides. And there is another example we have seen, if there is a stratified the flow, like the two fluids are going, if I want clustering in between, right? And how to have clustering at a particular location, and how to change the clustering. Those things we have seen different formulations that are existing in the literature. Okay, and also we have seen for if there is a supersonic flow over a blunt face. Okay, so how it can be done in both x direction and y direction, how to cluster them. So those examples we have seen. And then we have discussed about the elliptic grid generation. So we have computational physical domain, and we have xi eta computational domain. So I have to solve del square psi equal to 0 and del square eta equal to 0 to get xi equal to xi of xy, eta equal to eta of xy. Okay, so this is to be obtained. So this is to be solved in the physical domain, but because this physical domain is complex, I cannot solve these equations in the physical domain. Okay, so I have to transform into this. And we have seen that we get something like a xi minus 2b xi eta plus c x eta eta equal to 0, and a yzi minus 2b yzi eta plus c y eta eta equal to 0, where a is equal to some x eta square plus y eta square. B is equal to xj x eta plus yj y eta, and C is equal to xi square plus yj square. So these are to be solved in the computational domain. And because these are elliptic equations, so we have to use either point Gauss Seidel or point successive over relaxation, or line Gauss Seidel or line successive over relaxation, or ADA or ADA with over relaxation. So these methods are to be used. So what I have to do, I have to take central difference for this. So we know that how to take it. Just I am writing xi plus 1j minus 2xij plus xi minus 1j by delta xi whole square. This is xij minus 2b into xi eta. How will I get? I will get all four corner points of that. So positive xi plus 1 j plus 1 will be positive. Xi minus 1 j minus 1 will be positive. But other two will be negative. Xi minus 1 j plus 1 minus xi plus 1 j minus 1 by 4 delta xi delta eta. So plus c into xij plus 1 minus 2 xij plus xij minus 1 by delta eta whole square equal to 0, like this. Okay, if I want point Gauss Seidel, what I will do is I will write xij k plus 1 is equal to all this onto the right side at k. Okay, so I will do this point Gauss Seidel. And if I want to have line Gauss Seidel, I will put something xi plus 1 j k plus 1 plus xij k xij k plus 1 plus xi minus 1 j k plus 1 is equal to everything known. Okay, known values. So now this tridiagonal matrix algorithm, I have to solve it. Okay, this is the way line Gauss Seidel. And you know successive or relaxation, all those things we know, I am not discussing. So this equation only is to be modified in the way we want, whether it's LGS or PSO or LSO or ADI or anything. Okay, so this is the way we have to use the elliptic grid generation. And so the advantages, what we have seen is it is used for mainly closed. This is another thing I didn't tell, closed domain. Okay, so elliptic equations we always solve in a closed domain, and it smoothens discontinuities. And you can have clustering. How to have clustering? If I write del square xi equal to some p xi eta, and del square eta equal to some p xi q xi eta, and the p and q can be chosen in the way we want, and so these are clustering parameters. So in that way I can have clustering also. But when you come to disadvantages, normally elliptic solvers are slow, marching methods are faster, and what else disadvantages? Okay, cannot be used for open domains. Like this. And so we will discuss today what is called as hyperbolic grid generation.
Sir, in previous slide you have told about elliptic, no?
Yeah, elliptic. Okay,
Okay,
till
sir.
now I have discussed about last class things. Okay, today I will start hyperbolic grid generation. Is it okay? Whatever I have done till now in the last previous pages, right? These are all elliptic only, which we have discussed in the last class. Just I have revised it. Is it okay?
Yes, sir.
Okay. Okay, when you come to hyperbolic grid generation, the mainly why we go for hyperbolic grid generation is these can be opened for open domains. These can be used for open domains. And another thing is these use matching methods, which are faster. Okay, this is the main advantage why we go for hyperbolic grid generation. Okay, so there we are solving two equations for xi and eta, and here also I should have two equations because two variables are there. And so how to get these two equations? They are obtained from two constraints. Two constraints. One is called uh, orthogonality constraint, and another is called geometric constraint. Okay, so what is orthogonality constraint? Because I want the grid lines to be orthogonal to each other. Okay, so from that constraint I can get one equation, and geometric constraint we will see how to get that equation. So I want to have xi lines and eta lines orthogonal to each other. So first we will see the equation for a xi line. So dxi equal to xi x dx plus xy dy, right? This is the equation. And so if you want to have slope of xi line, right? So dxi should be 0. So what will I get from this? Dy by dx of xi equal to constant is equal to, if this is equal to 0, what will I get? Dy by dx
minus xi y by xi x.
minus xi x by xi y or xi y by xi x?
Psi x
Xi
by
x,
y.
xi x by
Xi
xi
x
y.
by xi y. Okay. So in the same way, d eta is equal to eta x dx plus eta y dy. And if I want to have dy by dx of eta equal to constant line, so this should be equal to 0. This also I will get minus eta x by eta y. So I want xi and eta lines are to be orthogonal. So those,
Product will be -1.
yeah, product will be minus dy by dx xi equal to constant, and dy by dx of eta equal to constant is equal to -1. So minus xi x by xi y into minus eta x by eta y equal to -1. So these two becomes plus. So I will get xi x eta x by xi y eta y. If I take it to the right side and bring it to this side, xi y eta y equal to 0. Okay, this is one equation. But these are having x and y derivatives, which are in the physical domain. I have to transform them into computational domain. I want to have xi and eta derivatives, not x and y derivatives. So I have to use the metric transformation. So if you remember, we have relations. Xi x is equal to actually 1 by xi. We will get x eta. And eta x is equal to minus 1 by j yz. And xi y equal to minus 1 by j x eta. And eta y into 1 by j x. Okay, like this we will get. So if I substitute here xi x into eta x, if I Did I write? No, I have written something. This will be y eta. Okay, like this. So if I xi x eta x means product of these two plus product of these two. So what will I get? J gets cancelled. I will get minus yj y eta minus xj x eta equal to 0, or xj x eta plus yj y eta equal to 0. This is one equation. This is what is called as orthogonality constraint. If I want to have the xi lines and eta lines orthogonal to each other, this equation is to be satisfied. Okay, I have to have the second equation. Second equation we get from the geometric constraint. There are two methods are usually used. One is called as cell area approach, and another is called as arc length approach. Okay, so what is, yes?
The previous slide, what is Jx is Jy neta, sir.
Yeah, here.
Jx is Jy neta, sir.
Okay, if it is j, everything will be j, otherwise everything will be 1 by j. As I told, it depends on the book. So you can use either j or minus j, but j's will be cancelled. Is it okay?
Sir. Okay, sir.
When you are substituting, j's will be cancelled. So it doesn't matter whether it is j or 1 by j. Okay?
Okay, sir.
Okay, cell area approach means we specify the cell area is specified. Okay, so as I told, cell area is nothing but Jacobian. So Jacobian is xj y eta minus x eta yj. So this is Jacobian. So 1 by j or j, okay, it doesn't matter. So this is specified as some f is equal to f xi eta. Okay, so this is the second equation. So cell area is specified. Okay, so this actually is a choice by which you can manage clustering. So this is also clustering parameter. Like this. So I have two equations now. Xj x eta plus yj y eta equal to 0. Xj y eta minus yj x eta is equal to f. Okay, so these two equations are to be solved. So if I want to solve it, again, I want the implicit method. If I want implicit method, so these are to be written as k plus 1, 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 like this. But when you write implicit method, what happens? This will become non-linear. Well, because two unknown values we are multiplying. So when we are having that, so I have to do some method of linearization.
Lagging.
Here we don't use lagging, we use Newton's saturation method. Anybody remember what is Newton's saturation method? A k plus 1, b k plus 1 is equal to, anybody remember?
So AK into BK plus 1.
Yeah.
plus bk into ak plus 1 plus
This
ak power plus 1 into bk plus
minus
1.
ak bk. Again,
Minus
plus
AK.
1 should not be there, right?
Yes.
These are known values. This is known value. Here, in these products, only one unknown will be there, so it becomes linear. Okay, this method is used to make it linear. So now you take one as A and another as B, and you have to write like that. So xi, here what I do is, superfix k plus 1 I will not write. Here I will not write k plus 1. It will be like akb plus bka minus akbk is equal like this. Why? Because these are unknowns. Okay, these unknowns I will not write any superfix. Okay, now how can I write xi k plus xi x theta k plus x theta xi k minus xi k x theta k. This is one plus yzi y eta k plus y eta yzi k minus yzi y eta k is equal to 0, like this. And if you see here, xi k x eta k plus yji k y eta k from this equation becomes 0. Because xi x theta plus yji y eta at any time it is 0. Right? So xi k x theta k plus yji k y eta k, these two together will become 0. So I will have these four terms. Okay, this is one equation. Okay, I will write again. Xi k x theta plus xi x theta plus yzi k y eta plus yzi y eta k equal to 0. Like that we get for this equation also in the same way. We will get xi k y eta plus xi y eta k minus xi k y eta k, these three, and yzi y x theta k plus yzi k x theta, it will become plus. No, minus only. No. Minus yzi k x theta, okay, is equal to f. And here xj k y eta k and minus yj k x theta k, this will become like minus fk, because is equal to f at k time. I will write the area is fk. So this minus fk, if I take it to here, it will become f plus fk on the right side, and these two will go off. So again, four terms will be there like this. Okay, this is the way we will write. Okay, I will show you the slides, because I can directly show the slides. I need not do this, but I thought you will remember if
Sir,
I do
not audible.
Not audible.
So you're audible.
Okay, it's okay.
Yes, sir.
Right. So here, this is the things. These are the things we have done. This is orthogonality constraint, and this is cell area approach 0f, and now this is one equation. This is another equation, and so again after this cancelling this, I am getting this, and this is the second equation. These are the two equations I will get. Okay, here I will write this in matrix form. Unknowns are xi, x eta, yzi, y eta, and these are coefficients. I will write this in this matrix form like this. So x and y. Okay, so I will write a into r xi plus b r eta. Okay, so x and y are to be solved, right? So here xi and yzi, coefficients of xi and yzi are here, and coefficients of x eta and y eta are here. And if I go back, so coefficients of xi and yzi are here x eta k and here y eta k. So x eta k, y eta k. In the second equation, here y eta k and yzi, okay, x eta k, okay. So y eta k and x minus x eta k, y eta k and minus x eta k. This is A matrix. B matrix, I have to write the eta derivatives coefficients. Okay, again go back. So x eta and y eta, right? So x eta k, x eta into x xi k, y eta into y xi k. So these two will come to the first line, x xi k and y xi k. You can see x xi k, y xi k. In the second equation, this is x eta. Where is x eta? X eta is this. So coefficient is minus y xi. Here coefficient is x xi k, y xi k and minus y xi k and x xi k. Minus y xi k and x xi k. Like this I will get. Okay, so this is the way I will write it in the matrix form. And right hand side I have 0 and f plus fk. And if I want to find out what type of equations these are, I want to show that these are hyperbolic equations. And for the hyperbolic equations, what I do, I have to find out, it is something like, I have A, R, I.
Sir,
Yes.
sir, there are some problem in audio sometimes ago.
Maybe it with you only, I think, because no other person is complaining.
No, sir. Even I have the problem.
You also have problem.
Yes, sir.
Sir, I have also problem.
Okay, okay. Shall I quit and again join?
Now okay, sir. Now okay.
Now okay.
Yes, sir.
Yes, sir. Yes, sir. Now okay.
Because I didn't do anything. I'm just doing as it is. Is it okay now? So shall I continue?
Yes, sir. You can continue, sir.
Okay. So here we have the equations like this. And how to find out whether it is elliptic, parabolic or hyperbolic? There are two methods. Like one is we will write t is equal to a dx plus b dy equal to 0. This is one way. Right. The other way we use, what I will do, multiply by here I will write like this. I just change it, b r eta plus a r xi is equal to h, and multiply by b inverse. I am going to get r eta plus b inverse a r xi is equal to b inverse into h. Okay, so how to find out whether it's elliptic, parabolic or hyperbolic? I have to find out the eigenvalues of this man. Okay, B inverse here. Okay, so what is B matrix? B is equal to xj yj minus yj xj. Xj yj minus yj x. Okay, this is B, and I can find out the inverse. So 1 by the determinant of B into the exchange these two, it will be xj only, and so minus yj here and yj here. This is B inverse into A. A is x eta y eta minus x eta. X eta y eta minus x. Okay, now I have to multiply this and I have to show get the eigenvalues. This is the way we will get. Okay, if I multiply that B inverse and A, I'm going to get this particular one. Okay, and if I find out the eigenvalues, I'm going to get this root of x eta k square plus y eta k square by the denominator is this. If the denominator is positive, if there is no problem, that is if it is not zero, no problem, then you can see that these are real. Okay, this is something square plus something square under root. Okay, so plus or minus. So the eigenvalues are real and the equations are hyperbolic. It is just to show that the equations that we have got are hyperbolic equations. And once we get understand that these are hyperbolic equations, and I have to solve them using matching method. So I have r eta plus d inverse A r z is equal to d inverse H. Okay, this is the way I got. This using matching method, how can I discretize it? This I will discretize it as R matching. It is like time coordinate, right? So Ij Rij minus Ri minus 1j by delta eta plus this D inverse A is some m I will write like this. And Rj, how can I write? Because this is central difference. X Rij, Ri plus 1j minus Ri minus 1j by delta z, 2 delta z. Okay, so in this way, I have to write it like this. Okay, the inverse H. And this, okay, these are known, it is like marching, no? So unknown values will be at the behind line. I have to find, using those line values at the behind line, I have to find out in the next line. It is like marching, space marching. It is not time marching, it is space marching in the eta direction. Okay, so that is the way we are going to do. So A and B inverse are calculated at j minus 1 grid line, and I am going to calculate the values at j grid line. And if you take delta z and delta equal to eta equal to 1, so I am getting this particular equation. Okay, so something into Ri minus 1j, something into Rij, and something into Ra plus 1j is equal to like this. So this is again, you are going to get block tridiagonal, which are to be solved. Okay, this is the way I have to go about the hyperbolic grid generation. Is everything clear till now?
Yes, sir.
Okay. And this is one method. The other method is arc length approach. So previously I have assumed some null area. Here some arc between 2 points. Okay, that length is to be assumed. It is like arc between 2 points is dx whole square is dx whole square plus dy whole square, and dx whole square I will write so dx I will write it as x xi x dx dx dou x by dou xi into dz. Okay, x xi dz plus x eta d eta whole square plus y xi dz plus y eta d eta whole square. This is the way we get. And if dz equal to d eta equal to 1, I will get this as xj plus x eta whole square plus yj plus y eta whole square. So this I will get as xj square plus x eta square plus 2 xj x eta plus yj square plus y eta square plus 2 yj y eta. And these two, if I combine, what will I get? Xi square plus x eta square plus yj square plus y eta square plus 2 into xj x eta plus yj y eta. And if you remember, this is orthogonality constraint, which is equal to 0. So this is what we get. So dx whole square is equal to xj square plus x eta square plus yj square plus y eta square, like this. So if I express the arc length along xi line or eta line, I will take only one of them. Okay, so along the lines of constant xi, xj and yj are 0, and x eta square plus y eta square is ds square. So along xi equal to constant line, if I give the ds along x eta line, sorry, okay, y eta square, like this. This becomes the second constraint. This becomes the second constraint. And the first constraint is same, xj x eta plus yj y eta whole square is the first constraint from orthogonality. And here x eta square plus y eta square is equal to delta s ds whole square. This is the second constraint, which is from arc length approach. Okay, this is the way I get. Again, this is also non-linear. This I will write as x eta plus y eta is equal to ds whole. Same thing again, that linearization I have to use, Newton's linearization. And same procedure is to be repeated. This you take it as homework. Okay, how we have to go about and what type of matrices you get, and how to show that it is a hyperbolic, and what is the way you have to solve it. The same way what I have done for cell area approach, you do for arc length approach. Okay, so take this, linearize, and get the matrices, and show the equations are hyperbolic, and the method of solving using marching. Okay, this you try using the same method that we have done for the arc cell area approach. Okay, whatever we have written for this, okay, the same way you have to do for the arc length approach. Okay, that you take it as homework. Okay, this is the way we do the hyperbolic grid generation. Then the main thing, if you compare parabolic and hyperbolic, elliptic and hyperbolic, okay, these are used for closed domains, these are used for open domains, and these are slower, these are faster, and it makes the discontinuities smooth because of second order derivative. Okay, So here what people thought is they want to come with a method where this advantage and this advantage can be utilized. Okay, where I can have both the advantages. And that led to the idea of parabolic regeneration. So that is, I have to use marching method to solve it, and I should have second order derivative in it. Okay, so you know the hyperbolic equation like ut is equal to nu uxx or tt is equal to alpha txx. Like that, we have second order derivative and first order derivative along which we march it. I have
Sir, you are
diffused,
combining both the advantages of elliptic
yeah,
and hyperbolic.
elliptic and hyperbolic. That we will get from the parabolic regeneration. Okay, so okay, this is written here, whatever I told. And the parabolic grid generation, the boundary discontinuity does not propagate and it will be smooth distribution and it will be faster. Okay. Okay, this is the way we take the equations. X theta minus a x z is equal to some sx. Y eta minus y z is equal to sy. Okay, so this is the one, and a sx sy they can be chosen. Okay, so depending on the orthogonality or clustering, xx and sy are source terms, and a is a specific constant. They are to be properly chosen for clustering and orthogonality. And the boundary grid points are specified on the surface, and matching procedure is used to solve the equations similar to that of hyperbolic systems. And grid point clustering and orthogonality is similar to that used in the elliptic system, may be enforced. Okay, so because of that, I have both the fast advantage, speed advantage, and also I have a diffusion term like second order derivative, which makes the discontinuity smoother. But as I told, this is in still research area only. It is not completely developed. So still people have not yet widely used this parabolic grid generation. So widely used one is elliptic grid generation, which is widely developed. Because whatever is developed means some routines are available, functions are available. I can just call them and use them. Okay, that's why people are comfortable whichever are developed. Okay, that is the main advantage of developed systems. But if you want to have go for a research and all, then we can take up this particular type of topic and we can do it. Okay, this is about grid generation. Any questions? Okay, with this actually structured grid generation, I conclude. And almost except for few topics here and there, we have covered the Hoffman first volume. So the next things that we are going to have is unstructured grid generation. And then we discuss about the finite volume methods. Finite volume methods again for structured grids and also unstructured grids. So dealing with structured grids is to write code by ourselves. And unstructured grid we learn because this is used in the packages which you are going to use for your projects, and even after your placement also, most of you people will be working with packages which are developed for unstructured grids with finite volume method. Okay, so though we don't know the concept of unstructured grid and finite volume method, you can use the package. I think we are using Fluent without knowing what is finite volume method and what is unstructured grid. Okay, how it is generated, you need not know because package will take care of. But because when you are using package, you should not use it like a complete black box. So you have to know what exactly is happening inside. Okay, for that purpose, we will learn.
Sir, voice is not coming.
Okay, is it okay now? Hello?
Okay, sir.
Right. Okay, so that's why we discuss finite volume methods, and both for structured grids and unstructured grids. And we will see some applications. Okay, this is the way we will plan the remaining time. Okay, with this, I close the structured grid generation. If there are any questions, we'll discuss. Otherwise, we'll go for the story. Anything?
Yes, sir.
Okay, so we'll go for the story then. And this is again real story, right? In England in 1920, there was a graduation ceremony for a batch of new doctors. It is like a convocation, right? And it was attended by the prime minister of that time. So here also we try to get the PM or president or something like that. Normally, many IITs try to get like that. And during the ceremony, the head doctor who was in charge of that batch gave the necessary advice to these new graduates. He told them the following incident which happened with him some time back. It was after midnight and I heard a knock on my door. It was an old lady and she said to me, "Oh, my doctor, my child is sick and in a very serious condition. So please do something to save him." I rushed out to follow her to her house without worrying what will happen because he has nothing and he has no instruments and all. But first to see the patient, he immediately went in the night. And because it was a stormy night and very cold, the rain was pouring down very heavily. I did not fear for my life. Her house was on the outskirts of London, and after a difficult journey, we reached her house. She lived in a small room with her son. When I entered the room, I saw her son at the corner of this room, groaning and deeply in pain. After I did my duty towards the sick child, the mother gave me a small bag with money. I refused to take this bag and I told her gently that I can't accept that payment because I felt sorry for their situation. Then I promised her that I will take care of her child until he gets better. The head doctor continued in his speech and by saying, "This is the true profession of medicine, and being a doctor is the closest profession to mercy and the closest to God, one of the closest to God." As soon as the head doctor finished his speech, the prime minister jumped out of his seat and headed to the podium. "Permit me, sir, to kiss your hand. For 20 years now, I am looking for you. I am the child you mentioned in your story just now. Oh, my mother will be happy now and she will rest in peace. Her only wish was for me to find you and reward you for the goodness you did for us at the time we were living in poverty." That poor child who became the Prime Minister of England was Lloyd George. Okay, he told it seems it really happened. Thank you very much. Thank you.
Sir,
Yes.
sir, I have a question. Can I ask regarding the CFD questions?
Yeah, yeah. CFT only we are talking, right?
Sorry, sir. MATLAB, sorry.
Okay. Tell me.
Sir, actually, in scheme beam warping implicit method, no, sir.
Yeah.
So in that method, sir, A of I, sorry, A, you said that it is Jacobian. A is equal to U, sir. So, sir, you have
Yeah,
not
it's equal
taken,
to you.
yes, sir. But, sir, you have not taken A is equal to U in the, sir, code. Can you show that code, sir?
Okay. If I don't take, you take it because that is right thing.
Yes,
I
sir.
might have done mistake. Okay. I might have done mistake, but A is you only.
Yes, sir. Sir, you have taken only
You
C.
old.
Sorry.
You old. Okay. So
Yes,
you
sir.
will. Okay. Okay, I will check it. Okay, I will check it and see. But okay, I might have done mistake. It doesn't mean that whatever I have written, whatever I have done are right. Okay.
No, sir, it is not. I mean, but I'm asking that it should be there or not. I
Yeah,
am
it
doing
should be there.
something
If
wrong.
A is there, in the place of A, you should have U.
Yes, okay.
A is Jacobian, and Jacobian is U only,
Yeah, okay, sir.
right?
Okay, sir.
Okay, I will see if I have done mistake. I will make.
Am I audible, sir?
Sir got disconnected, I think.
Yeah, I think also.